Hello, I'm going to go ahead and talk through Unit 3.3 again. And appreciate that some of you haven't seen different instruments or thought about them before, and I want to try to make sure we get all of the need to know information out very clearly, because I know sometimes in class we're just enjoying the performances too much. Well, not too much, but we are enjoying them. Okay, so let's go ahead and talk about mechanical reed instruments. What do we mean by that? We mean the clarinet, saxophone. Okay, those are single reed instruments, and then things like the oboe and the bassoon and the English horn. Okay. So in all of these cases, the excitation is blown air, and the oscillator is the vibrating reed. The reed is either a single reed against a mouthpiece or a double reed, just two reeds together. They flap open and closed like you saw in your learning activity with the straw. The filter and resonator in all of these is the tube plus the mouthpiece. And then the radiator is primarily the tone holes, the open tone holes, that is. Okay, so typically these instruments, okay, like a clarinet, it has a series of holes going down the body. And then to make different tube lengths, this is the mouthpiece end, then you would cover or uncover those different holes to make different lengths. So if, for example, if they were all closed, right, then you would have a tube the whole length L. But if only a few of them are closed, then the effective length is much shorter. Okay, and so this would be a shorter L, which would produce a higher note. Okay. Now with that tube shape, so closed on the mouthpiece end and open at the tone holes or the other end, you have the clarinet. Okay, so the clarinet is modeled as a closed open tube. Sorry. A closed open cylindrical tube, meaning it's like a cylinder, meaning it's constant width all the way down. Okay. And it will have the odd harmonics in the sound. What we mean by that is we're saying that our closed open tube model works. So for a tube closed at one end, open at the other end of length L, the first natural frequency or resonance of the tube F1 is V over 4L. The second resonance or natural frequency of the tube is 3 times that, and the third one is 5 times that. So you have a V over 4L for the lowest resonance or natural frequency, and then you go up higher on those others. Okay, and that is this equation right here, V over 4L with odd harmonics is for the cylindrical open closed tube that is a good model for the clarinet. What makes the sound reflect at the open end? Okay, so if you imagine a puff of air traveling down that tube, it is constrained to within the tube, and then all of a sudden it's not at this open end. And that causes some of the air escapes, okay? But some of the air will get sent backwards, actually the pulse will be upside down, and then it hits this hard end, so it reflects back the same way it got hit. When it hits that open end, it will reflect upside down from what it was, and so then it will complete the whole cycle. Okay, so for the open closed tube or closed open tube, same thing. the vibration, the pulse, whatever you want to think of, the puff of air travels 4 lengths of the tube in one cycle. Okay, and that is why we have F1 is V over 4L, because that's how much it must travel to complete a whole cycle. And again, it's the interference between these reflected waves, the incident and the direct and these other reflected waves that cause standing waves in the tube or natural modes. And so that is what is supported by the tube. The tube will amplify those. And in the case of clarinets in particular, it determines the pitch that will be played, which we'll talk about here in Roman numeral number 3 in just a second. Okay, so number 2, describe the relative strengths of high and low frequency energy in a wind instrument when it is blown loudly and when it is blown softly. Okay, so the answer is D. Okay, so when you're softer sounds, lower volume, lower intensity sounds, okay, just like we saw with the vocal folds, there is a smoother motion of the reed. Okay, which results in or produces a smoother periodic waveform. Okay, but louder sounds have a more abrupt motion of the reed. Okay, which will be more jagged or more abrupt. Is jagged a good word? With steep portions. Okay, and that jagged or steep wave corresponds to more high frequencies. Okay, so this smoother periodic wave will be a warmer sound. And that means more low frequencies, or mostly low frequencies. Low frequency partials in this, making up the sound. Whereas this jagged steep wave, it will be a brighter sound. And it will have more energy in high frequency partials. And we're going to revisit this concept basically with every musical instrument. Sorry. All right, so the green is basically how the source and the excitation are, and then the purple is what that does to the sound. Okay, so this next question, number 3, is talking about the coupling between the oscillator and the filter. Okay, that's what it's talking about. So in the voice, there is the least coupling because you can sing any pitch on for any vowel, right? So the vowel is the vowel, that vocal tract shape, which is your filter. So for a single filter, ah, I can do I could do any pitch I want. So there's very little coupling between the pitch, the vibration rate, okay, so lip reeds and saxophones can bend the notes a bit, but mechanical reeds, most of the mechanical reeds have very strong coupling. And by coupling, another word for coupling would be influence. Okay. Well, let me write it this other way. A strong coupling between the vibration of the reed or the oscillator and the tube configuration, meaning the length and open tone holes and things like that. And what does that mean? That means that the vibration rate or frequency must match, must match one of the natural frequencies of the tube. That's what strong coupling or strong effect about between the vibrating air column and the reed motion. It's just different ways to say that. Okay, so to be able to maintain the same fingering, okay, so same fingering means same L, okay? So we're doing the same length for our tube. We're talking right now about the clarinet. The clarinet, again, was our open-closed tube of length L, closed on the mouthpiece end, open on the bell end. Okay, let's just say that's the length to the first open tone hole. And then to have that same length play a higher note. Okay, so we have again, F1 is V over 4L, and then F2, the second natural frequency of the tube is 2F1. Okay, so when the clarinetist opens the register key, meaning they put the register hole, they push down on the key and open the register hole. Okay. And they match their blowing rate. Sorry, this should be 3F1. So they have to blow faster. And access or sound the second natural frequency of the tube. Okay, so instead of playing the pitch of V over 4L, say that's 260 middle C, then they would do F2, which would be 3 times that, which would be roughly 780. Okay. So that's for the clarinets. Okay. So this summary table, okay, hopefully as we're going through these different categories, it will be helpful for you to keep referring to this, to be able to know what's going on. But remember, for the clarinet, which is this mechanical reed number 1, when you open the register hole, the note goes up by a 12th. But for this other case, these ones that are more cone-shaped tubes where you have all the harmonics because of that tone shape, when you open the register hole, it goes up by an octave. So in factor of 2. Okay. Good. Well, hopefully that is helpful. Please think of your questions so that we can get those answered as well.